We have learned how sequences like strings, lists, and tuples store multiple values in order. The next important skill is learning how to extract just the part we need. This is where slicing comes in. Slicing allows us to take a portion of a sequence by specifying a range of positions. It is a simple concept, but it is extremely useful in programming because it lets us work with specific pieces of data instead of the entire sequence. In this lecture, we will learn the basic slicing syntax, how start and stop positions work, and how slicing can make our code more efficient and easier to read. Before we dive deeper into slicing, we need to review two key concepts: iterables and indexing. In Python, iterables are objects that we can loop through, meaning we can access their elements one at a time. Common examples include strings, tuples, and lists. Each element in an iterable has a specific position, which we call its index. The index tells us where that element is located within the sequence. Indexing is the way we use those positions to access individual elements. This concept is very important because slicing is built directly on top of indexing. Once we understand how indexing works, slicing becomes much easier to understand. The syntax for indexing is very simple. We use square brackets after an iterable, and inside the brackets we place the index number. So when you see something like iterable bracket n, it means we are accessing the element at position n. This allows us to retrieve a specific item from a sequence, such as a character from a string or an element from a list. Let's look at a simple example of indexing in action. Here we have a list called fruits that contains several items. Each item in the list has an index, starting from 0. When we write fruits bracket 0, we are asking Python to give us the first element in the list. So when this code runs, it will print apple, because apple is located at index 0. This example shows an important rule in Python. Indexing always starts at 0, not 1. This is another example. This time, instead of index 0, we are using index 3. Remember, indexing starts at 0, so index 3 actually refers to the fourth element in the list. If we count, apple is 0, grape is 1, orange is 2, and guava is 3. So when we run this code, it prints guava. Let's see what happens when we use an index that is out of range. In this example, we are trying to access fruits at index 5. However, this list only has 5 elements, and the valid indices go from 0 to 4. Since there is no element at index 5, Python raises an error called index error, list index out of range. This means we are trying to access a position that does not exist in the sequence. It's important to always make sure your index stays within the valid range of the sequence to avoid this type of error. So far, we have been using index numbers to access elements. But sometimes we don't know the position, we only know the value. The index function helps us find the position of a specific item in a list. In this example, we use fruits.index with apple and banana. Python searches the list and returns their positions. So apple is at index 0 and banana is at index 4. This is very useful when you need to locate an element before working with it, especially when the position is not already known. Negative indexing allows us to access elements starting from the end. An index of -1 refers to the last element. -2 refers to the second to last, and so on. In this example, fruits bracket -1 gives us banana. Fruits bracket -3 gives us orange. And fruits bracket -5 takes us all the way back to apple. Negative indexing is very useful when you want to access elements from the end of a sequence without needing to know its exact length. Now let's take a look at sequence slicing. Slicing allows us to create a new sequence by extracting a subset of elements from an existing one. The result is a new sequence of the same type, and the original sequence remains unchanged. In this example, we have a list of numbers, and we use numbers bracket 2:6. This means we start at index 2 and go up to index 6. But importantly, we do not include the ending index. So Python returns the elements at indices 2, 3, 4, and 5, which gives us 5, 7, 11, and 13. A key point to remember is that slicing includes the start index, but excludes the end index, and it always creates a new sequence without modifying the original list. The general format is iterable bracket start index colon end index. The start index tells Python where to begin the slice, and the end index tells Python where to stop. The start index is included, but the end index is not included. So this syntax allows us to select a range of elements from a sequence in a very simple and readable way. Understanding this format is important because we will build on it to create more flexible slicing operations. Let's look at what happens when we only specify the ending index in a slice. When the start index is omitted, Python automatically assumes the starting position is 0. So when we write numbers bracket colon 6, it means start from the beginning of the list and go up to index 6, not including 6. That's why this gives the same result as writing numbers bracket 0 colon 6. Both expressions return the first 6 elements of the list. This shorthand makes slicing more convenient and keeps your code clean and easy to read. When the ending index is omitted, Python automatically goes all the way to the end of the sequence. So when we write numbers bracket 6 colon, it means start at index 6 and continue to the end of the list. That's why this gives us 17 and 19. This is the same as writing numbers bracket 6 colon length of numbers, but the shorter version is much cleaner and easier to read. This shorthand is very useful when you want everything from a certain point to the end of a sequence. When you omit both the start index and the end index, Python returns a slice that includes the entire sequence. In other words, when we write numbers bracket colon, Python creates a copy of the original list. So the result looks exactly the same as the original, but it is actually a new list stored separately in memory. This can be useful when you want to duplicate a sequence without modifying the original. Let's briefly talk about shallow copy versus deep copy. A shallow copy creates a new object, but it only copies references to the elements inside. A deep copy, on the other hand, creates a completely independent copy of both the object and all of its elements. In this example, we create a copy of the list using slicing with brackets colon, which produces a shallow copy. However, when working with only primitive data types, such as integers, strings, or floats, shallow copy and deep copy behave the same way. This is because primitive values are immutable, meaning they cannot be changed after they are created. As a result, even though a shallow copy references the same elements, any modification actually creates new values rather than changing the original ones. In practice, the original list and the copied list remain independent. The difference becomes important when the list contains mutable objects, such as other lists or dictionaries. In those cases, a shallow copy shares references to inner objects, while a deep copy creates completely independent copies of everything. In this example, we create a copy of the list using slicing with brackets colon, which produces a shallow copy. At first, both the original list and the copy look exactly the same. Then we update one element in the original list. Guava is changed to mango. When we print both lists again, you'll notice that only the original list has changed, while the copied list remains the same. When working with primitive data types like strings, this behaves just like a deep copy because these values are immutable. Let's look at an example where shallow copy behaves differently. Here, our list contains a nested list. Notice that guava is inside its own list. We create a copy using slicing, which produces a shallow copy. At first, both lists look the same. Then we modify the inner list by changing guava to mango. When we print both lists again, you'll notice that both the original and the copy have changed. This happens because a shallow copy creates a new outer list, but the inner objects are still shared between both lists. So when we modify the nested list, the change is reflected in both. This is where shallow copy and deep copy are different. A deep copy would create completely independent copies of the inner objects as well, so a change in one would not affect the other. In addition to start and end indices, we can also specify a step value using a second colon. The syntax becomes iterable, open bracket, start index, colon, end index, colon, step, close bracket. The step tells Python how many positions to move each time when selecting elements. In this example, we use numbers, bracket, colon, colon, 2. This means start from the beginning, go to the end, and take every second element. So Python skips one element each time and returns 2, 5, 11, and 17. Using steps gives us more control over how we extract elements from a sequence. When we use a negative step, Python moves through the sequence in reverse order. In the first example, numbers bracket colon colon -1 means start from the end and move backward one step at a time. This reverses the entire list. In the second example, we are more explicit. We start at index -1, which is the last element, and move backward to index -9, stepping by -1. Again, this produces the same reversed list. Using negative steps is a powerful way to reverse sequences or traverse them from the end toward the beginning. Slicing is not just for retrieving elements. We can also use it to update parts of a list. In this example, numbers bracket 0:3 refers to the first 3 elements of the list. We then assign a new list to that slice. As a result, the elements at indices 0, 1, and 2 are replaced with 2, 3, and 5. The rest of the list remains unchanged. This shows that slicing can be used not only to extract data, but also to efficiently modify multiple elements in a list at once. In this example, numbers bracket 0:3 refers to the first 3 elements of the list. Instead of replacing them with new values, we assign an empty list. This effectively removes those elements from the list. So after this operation, the first 3 elements are deleted, and the remaining elements shift forward. This shows that slicing can also be used to remove multiple elements from a list. Let's look at more advanced ways to modify a list using slicing. In the first example, we use numbers bracket colon colon 2, which selects every second element in the list. We then assign new values to those positions. As a result, every other element in the list is replaced with 100. Notice that the structure of the list stays the same, but specific positions are updated. Next, we use numbers bracket colon equals empty list. This removes all elements from the list. The important detail here is that the list itself is not replaced, it is modified in place. We can confirm this using the ID function. Before and after the operation, the memory address stays the same. This shows that slicing can be used not only to modify parts of a list, but also to update or clear the entire list while keeping the same object. In contrast, in this example, we assign numbers equal to an empty list. This creates a completely new list object. When we check the ID again, we see that the memory address has changed. So the key difference is this. Using slicing clears the existing list in place, while assigning a new empty list creates a brand new object. Today, we explored how slicing allows us to extract, modify, and manage sequences efficiently. As you practice, focus on understanding how indices, ranges, and steps work together.
Thank you for your attention today. This presentation was prepared by
Jun B.
with assistance from AI Technologies. I truly appreciate your engagement. See you in our next class.